Welcome to A-Star Science, part of our GCSE Must Know Chemistry series. Today we're going to be talking about the periodic table, the modern periodic table, and the periodic table is the most basic, most important knowledge that a chemist and the students in GCSE chemistry must have. Even the most modern and advanced chemists use the information found on the periodic table. So it's very important for students to understand this as the basics. So let's first look at how the periodic table is organized. The modern periodic table is organized going across the periodic table horizontally in groups. So this is group 1, this is group 2, group 3, 4, 5, 6, 7, and 8, which group 8 can also be called group 0. Now, the groups represent the valence electrons, meaning that's the valence in the electrons in the outer shell of those atoms in the periodic table. Let's look, for example, at hydrogen, which here is in group 1. It has 1 electron in its outer shell. We can also look, for example, at beryllium. Beryllium is in group 2. It has 4 electrons, 2 in the inner shell, and then another shell, it has 2. Like so, the X's represent electrons. This is why it's in group 2. So the valence electrons, or the electrons in the outer shell, correspond to the group number. You may be asking, well, what about group 8? Well, if we look at helium, helium has 2 electrons, and that means it has a full shell, so it needs no more electrons. So we call that group 0. It doesn't need any more. Or you can use another atom in group 0 or group 8, neon, which has 10 electrons, 2 in the first shell. That means it has 8 in the second shell. It needs no more electrons, so alternatively, we call it group 0 because it needs no more, or you can call it group 8. So that's the horizontal parts of the periodic table. As you go this way on the periodic table, again, we call those groups. Now, as you go down the periodic table, we call those periods. Periods represent the number of shells, energy shells, where the electrons live in an atom. So for example, if we look at hydrogen, which is this element here, it's in period 1. It has 1 electron, and so it has 1 shell. If I look at neon again, neon, which is in group 2, it has 10 electrons, so it has 2 in the first shell, and then we'll have another 8 in the second shell, showing that's why it's in period number 2. So the periods represent the number of shells, electron shells, energy shells, where these electrons live. Now, for the periodic table, you will see each atom, each element has a little box, a little home, and there's information in that. Let's use lithium as an example. Lithium has these 2 numbers in it, the number 7 and the number 3. The top number represents the atomic mass, the relative atomic mass. It's very important to state that. The bottom number represents the proton number. So let's start with the bottom number, the proton number. This number is also called the atomic number. The atomic number is how the periodic table, the modern periodic table, is organized. So hydrogen is the first one. It has an atomic number of 1, or proton number of 1. Helium has 2. lithium has 3, and so on and so on. The atomic number also tells you how many protons does that particular element have as an atom. So lithium, in our example, will have 3 protons, which are positively charged in its nucleus. The atomic mass is the number of protons and neutrons added together, because each one has a mass of 1. So you can use this information, atomic mass minus the proton number, to tell you the number of neutrons in an atom. So we can use lithium as an example. If lithium has 7 as an atomic mass and a proton number of 3, then it's going to give us 4 neutrons in its nucleus. 3 plus 4 equals 7. Now, previously, the atomic weight in very old periodic tables was how it was organized. The periodic table was organized. But the modern periodic table is organized by atomic number. Previously, the atomic weight was the way that they could find out about the different elements. But as they began to learn about more elements and they were able to look at their properties, they realized that organizing them by their properties, the number of protons was more important. We can see an example of this when we look at these 2 elements here. So if we look at these 2 elements here, we start with antimony, it goes to tellurium, and then to iodine. We can see an interesting pattern there. Here, the atomic mass is 122. For tellurium, it's 128. But this drops back down for iodine to 127. This shows that the atomic number is more important in the modern periodic table, which goes from 51 for antimony to 52 to 53. Now, what's the reason for this? The reason for this is that in this particular family, which we call the halogens, iodine is more like the ones in that family than tellurium is. So it was put into that family despite its atomic mass not following that pattern. So the modern periodic table, just to summarize, is organized by atomic number. Previously, the older periodic tables were organized by atomic weight. Now, we use the term relative atomic mass. And this is important to understand. For your GCSE, you will tend to see different numbers than the one I have on this periodic table because they are rounded up. Why? It's because atoms exist as multiple types, which we call isotopes. So let's look at that really quickly. So for example, if we look at hydrogen, for example, hydrogen can exist as something that has an atomic mass of 1, an atomic mass of 2, and an atomic mass of 3. In fact, I should write this like that. 1, 2, and 3. So these are 3 different forms of hydrogen. I know they're all hydrogen because their atomic number is still all 1. So that means that this hydrogen has 0 neutrons, this has 1 neutron, and this has 2 neutrons. This is what we call isotopes. So isotopes have the same number of protons, but different numbers of neutrons. That's the definition for isotopes, which is an important definition in your GCSE exams, different numbers of neutrons. So what scientists have done, because they all have different masses, which are in red, they've taken the average mass of that. And you'll see on my periodic table that the average mass is 1.01. Now, if you round that up, it's just 1. So round it up, it's just 1. And so this is the one that you tend to see on the GCSE periodic tables. Chlorine provides a good example of this because chlorine here doesn't have a whole number. It's 35.5. And that reflects that chlorine has different isotopes for it. So we need to understand that the term relative atomic mass comes from the fact that these atoms on the periodic table can have different isotopes, and the mass is an average of the occurrence of those different isotopes in nature. And it's something that you will have to also calculate, and you can look at my video on calculating relative atomic mass in the future. So let's continue with our investigation of the periodic table. Now, I mentioned this particular group, group 7, earlier, and I said that iodine was placed in this group because it has properties similar to the rest of the group members. We call that families in the periodic table. There are many families that exist in the periodic table. So I don't have much space, but I'll try to lay it out. In fact, I'll label it like this. So family A here are what we call the alkali metals. When you put these metals in water, they form an alkaline solution. Family B here are similar. We call them the alkali earth metals. They also form alkali solutions in water. They're not as reactive, some of them, as group 1, but they can be quite reactive, and they're all metals. This particular family here, we call the transition elements or transition metals. They're all metals, and they're not as reactive as the alkali metals and alkali earth metals. And they're very useful. You'll see some of the major metals that we use in this family, such as copper and iron, which we use for steel. If we continue to look, I already talked about the halogens, which I'll put here in purple. Those are the halogens, which is group 7. And they all have similar properties as well. They like to react, for example, with metals. And on the group 8, which I'll call D, we call these the noble gases, sometimes called the rare gases, because not much of them exist in the atmosphere. These are very non-reactive, and we're going to talk about reactivity in a minute. Now, the periodic table can also be separated into metals, non-metals, and a family that's between them, which we call metalloids. So if I use this color and I go down, I'm going to create like a stairwell almost that's going to go down. And on the left side, you're going to see where the metals are. These are what we consider metals, down to bismuth, all the way down to polonium. So this left portion here, we call metals, and metals have specific properties. In between that, we have another sort of staircase, which I'm going to include here, like so. We call these the metalloids. These are the metalloids, or semi-metals, we can call them. Let's shade that. So red is the metals, blue is the metalloids, also called semi-metals. And then finally, on this side here, which I've shaded in orange, we call these nonmetals. These all tend to be gases, most of them, but some of them are liquids and solids. So finally, let's talk about the reactivity of the periodic table, reactivity trends. You can watch my video on reactivity trends of the periodic table separate from this, which I go into more detail. Here, I will just be talking about the general trends. Now, as you go down on the left side of the periodic table, you tend to become more reactive. The elements tend to become more reactive as you go down. As you go to the left on the periodic table, that also tends to trend to be more reactive. Now for the nonmetals, it tends to work the opposite. As you go up here, it tends to be more reactive. Like so, more reactive. Some of the groups are not very reactive at all. So this sort of group 4 here, they are not as reactive as the other elements in the periodic table. And that also includes group 0 or group 8, because they have a full outer shell. They are also not very reactive. So something like francium, far to the left and far down the bottom as a metal, is extremely reactive. In fact, it doesn't really exist in nature, and when it does, it's so unstable that it quickly reacts with things that are around it. And on the nonmetal side, something like fluorine is incredibly reactive as well. So these are the basics of the periodic table. I hope the video was helpful. It includes the most basic things that you need to know to understand how the modern periodic table is organized. Please make sure you leave a comment. Do like and subscribe. Let me know if there's any video topics that you'd like me to do.